Statistics as estimators. We use sample data to compute statistics, and the statistics we use to estimate population values. So for example, we're going to estimate the population mean from the sample mean. In statistics, an estimator is a method for producing the best guess about a population value. An estimate is a specific value provided by an estimator. So we'd like good estimates. So if we're trying to estimate the population mean from the sample mean, we'd like to do that well. Statisticians have worried a lot about what makes a good estimator. How would you know that it's a good estimator? What properties should it have? So we're going to talk about that a little bit. The literature on this is actually much bigger than what we're going to discuss, but unless you're really interested in statistics, you would find it very boring. So we're not going to spend much time on it. All right, but a couple things we do need to know because you're going to run into them during your career as a psychologist. One of them is the principle of maximum likelihood. So to talk about maximum likelihood, we first have to tell you what a likelihood is. Likelihood is a conditional probability, the probability of something given that something else is true. So the notation for that is L for likelihood is equal to P for probability, and then probability in parentheses, the probability of whatever that is. The probability that X is equal to some value, vertical bar here, so that means given. Earlier on I showed you a semicolon there. So some people use a semicolon, some people use a vertical bar, but either way it means given. And then the Greek thing to the right of that vertical bar is theta. So the likelihood is equal to the probability that X has some value given theta. L is the, all right, next bullet, L is the probability that X has some value given that the parameter theta has some value. L1, for example, is the probability of observing heights of 68 inches and 70 inches. So there's two people, 68 and 70 inches tall, given that these were drawn from a population of adult males. L2 is the probability of 68 and 70 inches, given that they're drawn from adult females. So theta can be continuous or discrete. So it could be a value for males, could be a value for females, it could be inches, could be 1, 0, whatever, it doesn't really care. Okay. Now, suppose we know the function. So for example, binomial or normal, but not the value of theta. So principle of maximum likelihood is about finding the best guess for our parameter, and that parameter is theta. So that's what we're trying to do. Maximum likelihood principle says take the estimate of theta that makes the likelihood of the data maximum. So MLP, maximum likelihood principle, says choose the value of theta that makes this maximum. So here we have the equation, a likelihood of x1, x2, x sub n given theta. So this is the function of likelihood of data given theta. We want to find theta that makes this thing maximum. That is maximum likelihood. All right, to give you a concrete example with a binomial, suppose we have two values hypothesized for proportions of male grad students at USF. We're gonna just hypothetically say that the males are 50% or they're 40%. So we randomly sample 15 grad students from USF, and we find that 9 of those 15 are male. All right, so the binomial is a function, and if we say 50%, then the likelihood that we find 9 people who are male, and the proportion P, probability of male, is 0.5, with 15 people is this is the number of combinations, 15 things taken 9 at a time, and here's probability of 0.5 for the probability of male, probability of 0.5, probability of female, and it works out this equation. If we compute it, our probability, the conditional likelihood, the likelihood of finding 9 males if the truth is 50-50 is 0.153. The likelihood of finding 9 males if the probability is 0.4, given there are 15 people, is now we're going to 0.4 to the 9, 0.6. So these two things got to add up to 1. And that value is 0.061. So the maximum likelihood principle says this is a better guess because it's more likely. So take 0.5 over 0.4 because the data are more likely. Now, you wouldn't actually do that. I'm just an illustration, okay? What you would actually do is you'd say, well, I got 9 out of 15 who are male, and what's my best guess? And so you could compute a likelihood function using that binomial that I showed you for each value of um, uh, theta. And what you see here is that maximum point is when theta is 0.6. So if theta, if the proportion of males is 0, you couldn't get 9 males and 6 females, right? If the proportion of males were 1, you couldn't get 9 males and 6 females because either it'd have to be no males or it'd have to be all males. So your best guess actually is 0.6 according to maximum likelihood. And 0.6 is 9 out of 15. So the best guess is to take the average. Now in this particular case, the common arithmetic answer and the maximum likelihood answer are the same, and you go, duh, why would I do anything else? But there are going to be times when you're running into computer programs that use different arithmetic functions. So you're going to see there are different ways of defining goodness, and different programs will give you different answers depending on whether they're maximum likelihood or their bootstrap or their ordinary least squares. You're going to run into different things. And so you should know maximum likelihood is one of the principles of goodness that statisticians like. So there's a general class of maximum likelihood estimators. And they find values of theta that maximize the likelihood of the sample result. So there's one principle of statistics. All right. So here's another principle that, in addition to maximum likelihood, that is you're going to hear a lot, and that is bias. Bias of a statistic is a property of the sampling distribution. So if the expected value of the statistic equals the parameter, the estimator is unbiased. So the estimator results, is a way of computing a statistic. It's a way of estimating a population value. You're going to get a sampling distribution for that thing. If the mean of that sampling distribution is the parameter, then you have an unbiased estimator. So that statistic is unbiased if it results on average in exactly the right answer. If it's unbiased, the mean of the sampling distribution equals the parameter. The sample mean has this property. So the expected value of x bar is mu. The sample variance, on the other hand, is biased. So what that means is if we use the sample data to estimate the population value of the mean, on average, we're going to be exactly right. On the other hand, sample variance doesn't have that property. And I'm going to show you that in a second. But before I do that, I'm going to talk about a couple other measures of goodness. So that'll be efficiency and resistance. So here we have efficiency. So efficiency has to do with the size of the sampling variance. So now sampling variance has to do with how close the estimates in the distribution are to the mean. All right, so it's the sampling variance. We're looking at the sampling distribution. What you're looking for is a relatively efficient estimator. So what you'd like to have is a small variance, because if you have a small variance, that means that all the values, all the estimates are close to the mean of the distribution. And if that's an unbiased estimator, that means that your efficient estimator has some estimates that are right on average and that are close all the time. So more efficient statistics have smaller sampling variance, so they have a smaller standard error, and they are preferred because if the two estimators are unbiased, one is going to be closer than the other to the parameter on average. Sometimes we trade off bias and efficiency. So a biased estimator might be preferred if it's more efficient, especially if the magnitude of the bias is known, or the magnitude of the bias is small. Um, resistance is a property of a statistic that indicates the minimal influence of outliers. So the median is more resistant than the mean because it's less influenced by outliers. All right, so those are some properties of the goodness of estimators that statisticians talk about when they're trying to decide what we should use. Okay, so now we're ready to talk about the sampling distribution of the mean. The sampling distribution of the mean is unbiased, so the expected value of x bar is equal to mu. So we're talking about the sampling distribution of the mean now. The variance of the sampling distribution of means based on n observations, so we've got the v sub m, that's equal to sigma squared sub m, so that sub m means for the mean, is equal to sigma squared divided by n. So here we've got the variance of the raw data that's got a distribution that has a variance called sigma squared. So sigma squared here is the variance of the raw data. The variance of the sampling distribution of the mean will be that variance divided by n, where n is the sample size. If we looked at the variance of the dice, so 1, 2, 3, 4, 5, we took that variance and divided it by 2, we'd get that 1.225 value in our example with the dice. The standard error of the mean is sigma sub m, and that is equal to the standard deviation of the raw data, sigma, divided by the square root of n. So see that is in that. This is just the square root of that. So the standard error is the square root of the variance of the mean. Law of large numbers says that large samples produce estimates very close to the parameter. So if you get a big sample, your sample estimate should be close to the parameter, and that makes sense. The bigger the sample, the better the guess. All right, so there's the sampling distribution of the mean. We can get a small standard error if we have lots of people. Unbiased estimate of the variance. So if you're mathematically inclined, you can show that the expected value of the sample estimate of the variance, so this would be the sum of x minus x bar squared divided by n. So if we find the sampling distribution of that, and then we find the mean of that thing, that's the expected value here, that mean is equal to the variance in the data minus variance in the data over n, which is equal to, if we do a little rearranging, n minus 1 over n times the variance. So if this were just n over n times the variance, then we'd have an unbiased estimator. But it's n minus 1 over n. So the expected value is going to be a little bit too small if we just take this as our estimator, this s squared. All right, so sample variance is too small by a factor of n minus 1 over n. So as n gets large, of course, this thing will become 1, and so you can sort of forget about it. But when n is small, it could matter quite a bit. So the way we fix this is we, instead of using big S, we use little s, and that is n over n minus 1 times big S. So you see, this thing has just been turned upside down. And if we carry out a little algebra here, we can show that that results in x minus x bar squared over n minus 1. So the reason we have this familiar formula of x minus x bar squared over n minus 1 for our variance estimator is that it results in an unbiased estimate of the variance, which is good because we want to be right on average. So it turns out that the variance is unbiased, but the standard deviation is still biased. Most of our inferences are based on the variance, not the standard deviation. So for statistical tests, we're happy about the variance because we can make an estimator that is unbiased. Okay, So here we go. It's time to review again, and that review should be what's the principle of maximum likelihood, define bias, efficiency, and resistance, and is the sample variance, that is the sum of squares divided by n, a biased estimator. So the principle of maximum likelihood says choose as your parameter estimate that value which makes the sample data most likely. So we're going to have some function that relates the sample data to some underlying parameter that we don't know. And maximum likelihood says pick the value of theta, pick the value of that underlying parameter that maximizes the likelihood of the observed data. Define bias. Bias is a property of the mean of the sampling distribution. So if an estimator has a sampling distribution where the mean of the sampling distribution is the parameter, they're equal, then the estimator is unbiased. If it's not equal to the parameter, then the estimator is biased. Doesn't matter how far off it is, either it's biased or it's not. Efficiency is a property of an estimator that has to do with the sampling variance. So things are relatively efficient when they have smaller sampling variances. We like small sampling variances because that means that the estimates are all close to the middle. They're all close to, hopefully close to the parameter. And resistance means resistance to the influence of outliers. So if we have outliers, these deviant, distant data points, they can mess up our estimate and get us far from where we want to be. And so we'd like to have statistics that are resistant to the presence of outliers. And finally, is the sample variance, the sum of squares divided by n, a biased estimator? Well, yes it is. We have to divide by n minus 1 in order to get an unbiased estimator of the variance.